Good morning, Year 11. So today we've got a lesson starting a forces topic. So we're learning today about forces and interactions. Let's start with our KIP quiz then. So 1 to 5 on your mini whiteboards. And let's take 3 to 5 minutes for this. So just pause the video and come up with the key terms for this. And then let's mark your answers. So 3 to 5 minutes later, and let's go through the answers to these questions. So number 1, how easily a liquid flows. This is viscosity. So thinking of our water and our treacle. So treacle is more viscous, that means it will flow less easily, whereas water is less viscous and it'll flow more easily. Number 2 then, thermal decomposition of long alkanes into shorter alkanes and alkenes. This is cracking. So we're splitting up a long hydrocarbon into 2 shorter products because they are more useful. So it might be that they're able to ignite more easily or they're able to flow more easily. So that's why we do it. Number 3 then, the distance a car travels while the driver reacts. So that's the thinking distance. So we'll come on to this in the future, but that can be affected by how much sleep the person has had, how much caffeine they've been drinking, maybe they're under the influence and they shouldn't be driving. So all of these things can affect thinking distance. Number 4 then, the distance a car travels once the brakes have been applied to stop the car. This is the braking distance. So the driver has pressed the brakes and it could be that the braking distance is affected by the condition of the road. So are they driving on a nice smooth tarmac or is it gravel? Has it been icy overnight? So are the roads quite slippery and therefore it's harder to stop? Has it been raining? So all of these different things can affect the braking distance. And lastly then, the sum of thinking distance and braking distance is what we call the stopping distance. So we just add the thinking distance to the braking distance and that combined total then gives us the stopping distance, taking into account the reactions of the driver, the road conditions and the weather conditions, and you put all that together to come up with the stopping distance then. So marks out of 5 on your mini whiteboards. I hope you did well. Remembering you should be practicing from your knowledge organiser on a daily basis because we will still have exams this year that the teachers will mark and use to decide your teacher assessed grade. So you need to be thinking we've still got to study and work hard towards those exams. Right then, so today we're starting a forces topic. So we should get this done by February half term. So today we're learning about forces and their interactions. You need to know the difference between a scalar and a vector quantity, understand how vector quantities are represented, describe the interaction between pairs of objects which produce a force on each object, and then we need to recall and apply the equation weight equals mass times gravitational field strength. So we'll practice using that today. Okay, so first up then, scalar and vector quantities. Remember, we need to know the difference between the two. So a scalar quantity, as you can see, only has size or magnitude. So the example there is speed. So a car moves at 30 meters per second. It could also be something like temperature. So a temperature has only a size. It can only be, say, 37 degrees Celsius or 40 degrees Celsius. That's the only information you have about it. A vector then has size and direction. So the example here is velocity. So velocity is essentially speed, but with a direction given. So the example, an aeroplane is flying at a velocity of 180 meters per second due east. So let's imagine we're on a flight from New York back to London Heathrow. So we're flying east, and because we've got the direction, that means that this is not just speed, this is velocity. So we know how fast the object is going. It's going 180 meters per second, and we know the direction. And so if we know the direction, if we know, for example, that something is being pulled down by gravity, and we know the size of the gravitational force, and we know that it's being pulled downwards, that's the direction, therefore we have a vector quantity. Okay, just as a quick reminder, make sure you've clicked that you're here on the register so that we know that you're following. Okay, so carrying on then. So what I want you to do is write a paragraph to explain the difference between scalar and vector quantities. Include 2 examples for each. So I did give, in my verbal descriptions, I did give 2 examples for each. And you could use the sentence starter, a scalar quantity is defined as. I'm just going to flick back to this page so you can just take a moment to think. So a scalar quantity only has size, and another word for size is magnitude, but a vector quantity has size and direction. And you've got your 2 examples there, but I want 2 examples for scalar and 2 examples for vector. And I did mention 2 examples for each when I gave my original description. So you could always go back in the video if you were seriously struggling. So a scalar quantity is defined as, let's then say 3.5 minutes for this task. So pause the video, set yourself a little timer on your phone, 3.5 minutes, and then get ready to review your answer. Okay, 3.5 minutes later, and here is what you could have written. So a scalar quantity is defined as a quantity with magnitude only. You might at that point have written size only, and that's fine. So if you wrote with size only, that's fine. Whereas a vector quantity has magnitude and direction. And again, if you've written has size and direction, or if you said has both size and direction, that's also fine. So then our examples, we needed to give 2 for each. So scalar quantities include temperature and energy. And examples of 2 vector quantities could be velocity and displacement. But remember, the one I was talking about just earlier was gravity. So that's an example of a force. So if you've not written displacement, but you've written gravity or force, then that is obviously perfectly okay. And there are lots more examples for both. So you could have actually written other examples too. Okay, so energy could be another scalar quantity. It's got a size but no direction. There are obviously lots of different forces that have got directional sort of effects, so you could talk about those too. And this could be an example, by the way, this paragraph could be an example of your work that you could photograph and upload onto Google Classroom, or you could wait till the end of the lesson till all your work's completed and then just send the picture of your workbook then. Okay, so let's just clarify the difference between distance and displacement. So let's imagine you're wanting to go somewhere and you want to take a journey. The distance is the path that you would actually take, but the displacement is the difference between your start and end point. And this could be in sort of real life because there was a hill in the way or a road in the way or houses in the way. So you can't always just take a straight path. So if you imagine you've got, say, your house and a friend's house, think about the route that you would take. But if you had to draw it on a map, if, say, a bird was able to fly from your house to your friend's house, think of the direct route that they would take. But you couldn't do that. You couldn't walk through houses or fly over houses. So you have to go round various streets, cross roads, round roundabouts. It might be that they live quite a way away from you. So the distance is the path that you would take. But displacement is the distance travelled in a defined direction. That is the definition. It is a vector quantity, but I just think of it as the sort of difference between the start and the end point of your journey. And if you think to yourself, well, why not just take the green arrow to get from A to B? Let's just say, well, it might be that there's something in the way. It could be a building, a school, it could be a motorway, it could be a mountain, it could be a river, it could be an ocean. So you don't always take the most direct route, but the difference between the start and end point is the displacement. And sometimes the displacement can actually be 0 because you go somewhere and then you come straight back. So you come back to that starting point. And if that's the case, you could have travelled and say you might have, I don't know, walked to the shop and back, and that was 2 kilometres distance. But because you've come back to the same starting point and there's no difference in your start and end point, then actually your displacement will be 0 because you've come back to the same place. Okay? So how do we draw vectors? How do we show? We use an arrow, and the direction of the arrow shows us the direction the force is acting in, whereas the length of the arrow shows us the size or the magnitude of that force. So if you imagine gravity, we do our arrows pointing downwards. So the downwards tells us that the gravity is acting in that downwards direction, but the size of that arrow can tell us its size. So a smaller arrow has a smaller size, a bigger arrow has a bigger size. And you've got the example there that the green arrow is acting towards the left. So it's pulling that object to the left, and it's got a size of 20 newtons, because remember, newtons is the unit for force. Okay, so forces then we can split into contact and non-contact forces. So contact forces are where objects are physically touching. So if, for example, you imagine friction between a tyre and the road, so the two are in contact. Air resistance, you can have somebody parachuting and there would be contact between the parachute and the air. Tension, so whenever you stretch something or you try and push something out of shape, it has tension, but again, there's contact. Whereas non-contact forces, like it suggests, they are physically separated. So there are gaps between things. So you can have something having a gravitational force, like you could be, for example, sat on your chair right now, and if you lift your feet off the ground, there's a gap between you and the floor. And obviously you're being held up by the chair, but there is a gap between you and the floor. And if the chair was not there, then obviously you would move downwards, but there is a gap. So you have got that idea that you're physically separated. Electrostatic force and magnetic force. So we know with magnets, you don't have to be touching a magnet to feel its effect. So forces can be separated into contact and non-contact forces. Okay. What do forces do? Well, forces are defined as a push or a pull. It's a vector quantity, like we've said before, so it's got a size or magnitude and a direction. And the three things they do to objects are they change the shape of an object. So if you imagine you're chucking a tennis ball down at the floor, if you actually watch that in slow motion, and you can find videos on YouTube, it would squash the tennis ball and then it would bounce back. They can change the speed of an object, so air resistance can slow a moving object, and then change the direction of an object, so you can cause it to change direction. So time for some questions now. So work your way through these 7 questions. So you can pause the video and set a timer for 7 minutes, and then we'll mark in purple pen. So get your purple pen ready as well. So these can be done in your exercise book. So pause the video for 7 minutes. Okay then, so let's go through the answers. So which one of these was the scalar quantity? It's energy, because it only has a size or a magnitude, it doesn't have a direction. Number 2, which one of these is a vector quantity? So it has to be force, because force is the only one that has a size and a direction, or a magnitude and a direction. Number 3, what is wrong with this statement? A girl ran with a velocity of 8 meters per second. Well, it can't be a velocity as there was no direction. What it should have said was that a girl ran with a speed of 8 meters per second. Okay, there was no direction. We didn't know whether she was running north, east, south, or west, or towards us or away from us or whatever. There was no direction, so it wasn't velocity, it was speed. Number 4, a man walks 4 kilometers due north. Make a drawing to show this displacement. So at this point, I may have done a little stick man, and then I would have literally drawn an arrow pointing straight up. So a man walks 4 kilometers due north. So because of the north, that would then be obviously an upwards arrow. And also then I might have labelled the arrow with 4 kilometers as well. For question 5, the man then walks 4 kilometers due south. So you literally have got the reverse of your previous arrow, and he comes back to the exact same place, which is why his displacement is 0 kilometers. So if you end up in a different place, to where you started, your displacement will always have a value. But if you go somewhere, travel somewhere, and then come back to your original starting point, your displacement will always be 0. Question 6, what distance did the man travel? It was 8 kilometres, so it was 4k north and then 4k back down south. So 4 plus 4 is 8. So there you're seeing the difference between distance and displacement. And now we need to explain the difference between distance and displacement. So displacement is a distance with a direction added to it. So 4 kilometres north, that is a displacement. Okay, so I'm expecting to see pictures of these questions and marked in purple pen. Remembering, if you need to make corrections, you can pause the video now and you can add to your work. So gravity. So gravity, we can also call this weight. Weight is the force acting on an object due to gravity. So you can see in the picture, you've got a mass, you've got a person, and you've got a car, and they've all got different weights because obviously they've all got different masses. The force of gravity on Earth is due to the Earth's gravitational field. So the size of the planet will affect the size of the gravity or the gravitational field strength. So the moon, for example, being much smaller than planet Earth, will have a weaker gravitational field. And then we can use this equation to work out weight. So weight equals mass, and that would be in kilograms, times by gravitational field strength. So we're going to practice using this now. So here's the triangle. I know some people are not a fan of triangles, but I do quite like them. So you can see you've got the W for weight at the top, the M for mass on the left, and then the G for gravitational field strength on the right of the triangle. And in terms of units then, weight is measured in newtons with a capital N. The mass would always be in kilograms. Now, if you were ever given in a question the mass in grams, you would then have to do a conversion. So remember, in 1 kilogram, there are 1,000 grams. You should then be able to do a conversion between the two. And then gravitational field strength is a combination of those two units, if you notice. So it's newtons per kilogram. And you'll always be given that. So, for example, on Earth, we say that there's a gravitational field strength of 9.8, or sometimes it's rounded up to 10, but the question will give you that. You don't have to remember that. So what I might be doing now is I might be pausing the video and writing myself a revision card. So talking about the triangle, the word equation, the different units and things like that, putting that all on a revision card. So let's do a practice one together. So like I said, you will always be given G. So G is the gravitational field strength. On Earth, it's 9.8. Sometimes you may be given it as 10 because it's just been rounded up. So Sarah has a mass of 50 kilograms. What is her weight? So you're looking to do weight equals mass times gravity, which would be 50 times 9.8, and we get a final answer then of 490 newtons per kilograms. If the question asked you to work out the gravitational field strength, you would do the weight divided by the mass. If the question was asking for the mass in kilograms, you would do the weight divided by gravitational field strength. Don't say that G is gravity. It's not. It's gravitational field strength. Okay, so that's our practice example. And I just want you to take note of how it's been laid out. So I've written the equation, W equals mg. Then I've inserted the relevant numbers, so W equals 50 times 9.8, and then W equals 490 newtons per kilogram. So you've got the answer plus the unit. So that's the way you should be laying out your work. So time for some practice questions, 1 to 4. So pause your video, complete these. Remember, each time you need to show you're working, just like I did here. So it needs to look like this. But for these questions, so pause the video and have a go. Okay, so let's review these questions. So number 1 then, a man has a mass of 85 kilograms, so it's already in kilograms. What is his weight? So then weight equals M times G, which equals 85 times 9.8. Remember, you'll be given the 9.8. Sometimes it will be rounded up to 10, and that equals 833 newtons. Number 2, a suitcase has a mass of 18 kilograms. What is the weight? So same equation, W equals M times G equals 18 times 9.8, which equals 176.4 newtons, or you might have just rounded it down to 176, and that would be fine. And again, sometimes the questions will specify whether they want you to answer in a whole number or they want you to do it to one decimal place. Or even numbers of significant figures. So just be prepared to read the question and apply what it wants you to do. Number 3 then, calculate the total weight of a backpack of the mass 1 kilogram with books 2 kilograms and trainers with a mass of 1.5. So you've got to add all of those up to get your mass, so which would be 4.5 times 9.8, because that's the gravitational field strength on Earth, which equals 44.1 newtons, or if you were doing it as a whole number, 44 newtons. Question 4, an apple has a mass of 0.1 kilograms. What is its weight? So this time then we do 0.1 kilograms times by 9.8, and you have a weight then of 0.98 newtons. So hopefully you did okay on these questions, and we can always practice them again in the future if you need more help with them. Right then, let's think about something nice. So I know at the moment the concept of going on holiday isn't really in our minds. We don't feel like we can do anything at the moment, and we're locked in, and it's currently raining and pouring whilst I'm recording this video. But let's just imagine that your name is Kate and you'd like to go somewhere on holiday. So you're going to jet off to Europe. And you have this situation that everyone has. Your total baggage allowance is 20 kilograms, and you have to decide what you're going to try and squeeze into your suitcase and what you may have to leave behind. So Kate only has scales that weigh in newtons. So remember, to work out the weight in Newton, you have to do your mass times by the gravitational field strength, which at the moment, for this question, we're going to take it to be 10. We're going to round up 9.8 to 10. So determine the items that Kate can take on holiday to get the mass as close as possible to the baggage allowance. Remember, that baggage allowance is 20 kilograms. So what you're going to need to do here is you're going to rearrange the equation. So normally for weight, we'd say weight equals mass times gravitational field strength. But now we want to work out in kilograms the mass of these different items. So we're going to have to do 5 calculations, starting with laptop then. If I just verbally model it, to work out mass, you do the weight, so 45, divided by gravitational field strength, 10. So you would do 45 divided by 10, and you'd get a mass of 4.5 kilograms. Now you do that for each one. So in your book, you should have 5 calculations. So 1 for laptop, 1 for camera bag, etc. And then once you've done the 5 calculations, you need to decide what she has to leave behind. What items can she take and what will she have to leave behind? So is she going to be able to take her laptop, or does that put her over the baggage allowance of 20 kilograms? Okay, so 5 calculations, and then work out what she'll take and what she's going to leave behind. And I reckon this might even take you, 7 minutes. So just pause your video, get it done, decide what she's taking, and then let's go forward to the answers. Okay, so did you work it out? Now I have to admit, I didn't know whether she needed to take a jacket, but let's just assume she's going at this time of year and it's cold where she's going, so maybe that's why. But for the 5 calculations then, you should have the laptop being 4.5 kilograms, the camera bag 5.5 kilograms, the walking boots 2.5 kilograms, and the jacket 3.5 kilograms, and the biggest mass of all were her clothes at 10.5 kilograms. So what is she leaving behind? Her walking boots and her laptop. And I believe that this combination of items, so clothes plus camera bag plus jacket, is the only combination that will get her as close to 20 kilograms as possible. Now, I am a bit worried that Kate is going on holiday without any shoes. So hopefully in her clothes selection, she's got some trainers or flip-flops or something. But yeah, I'm a bit worried she's going without her shoes. But this seems to be the only combination that will get her as close as possible to 20 kilograms. If I'm wrong on that, and I'm happy to be wrong, then can you send me what you think is the best combination to get as close to 20 kilograms as possible? Okay. Right then, time for some mini whiteboard questions. So get your mini whiteboard out again. So what force causes the marble to fall down the track? So falling down, that's your clue. I'll count to 5. And you should have gravity, down being the clue. Okay, let's do a practice calculation question. So this one we're working out mass, which is weight divided by gravitational field strength, and see how the question has provided you with the gravitational field strength. So on your mini whiteboards, what would you do to work out mass? Okay, so you should have then done 6.4 divided by 9.8, which will give you a final result then of 0.65 kilograms. I just want to point out that in this question, they gave you the kg, but if they'd forgotten or they on purpose were not giving you the units, then it would be up to you to write the units to get full marks. Okay, another quick quiz on your mini whiteboards. So what is the unit for gravitational field strength? So from the 4 options on the right, what is the unit for gravitational field strength? Okay, and then you should have newtons per kilograms. So it was the bottom one, newtons per kilogram. It's easy to get sucked in by the G, thinking gravity, but that's not right. Okay, another question then on mini whiteboard. So what is the equation that links gravitational field strength, mass and weight? And I don't mind if you want to use just the symbols. And then second question, to calculate the mass of the ball. So how would you use the equation to calculate the mass when you've been given the weight and the gravitational field strength? So this is 4 marks in total, so you can pause the video for 4 minutes. Write down these answers on your mini whiteboard. Okay, so 4 minutes later, we were looking for this equation. So weight equals mass times gravitational field strength. If you wrote W equals M times G, or W equals mg, that would also get you 1 mark. And then to work out mass, you need to do weight divided by gravitational field strength. So that would be 1.4 divided by 9.8, and then a final answer of 0.143. And were the units included? Yes, so just 0.143 would get you 3 marks. Now, although it says allow 0.143 with no working shown for 3 marks, that's a really risky technique to apply in an exam. I would always show your working, because if you put one of the numbers in wrong, so say you accidentally put in 1.5 instead of 1.4, you would still get marks for the method that you'd applied. So just always please show your working. I know we go on about it all the time in science, and I'm sure in maths lessons as well. Okay, so you're done for today. Don't forget to take a picture of your work and then upload it onto Google Classroom or email it to us, and then we can tick that off for you. So thank you very much.